for coming to the tonight webinar. So my name is Xinzheng, and I'm having the honor to organize this webinar tonight. So before the beginning of the seminar, first I will give a brief introduction, brief introduction about IABSE and also the speaker. So firstly, I will give a brief introduction of IABSE. IABSE is the mission is to exchange knowledge and advance the practice of strategy worldwide. It covers more than 100 countries. And the IABSE is the short name of the International Association for Bridge and Structural Engineering. It is a scientific and technical association comprising members in 100 countries and accounting to 60 plus national groups worldwide. It was established in 1929 and it sits in Switzerland. And now the president of IABSE is Tina Verona from Denmark. So IABSE deals all aspects of structural engineering, from the planning, design, construction, operation, monitoring, inspection, maintenance, and all topics. And the term of structures include bridges, buildings, and all kinds of civil engineering structures composed of any structural materials. And the objective of and the tasks of IABSE is that to promote the collaboration and understanding among all those concerning with structural engineering and related fields by worldwide exchange of knowledge and experience, to encourage awareness and responsibility of structural engineers toward the social needs, to encourage actions necessary for progressing in structural engineering, and to improve the foster cooperation between organizations have similar objectives. For this purpose, the association organized conference worldwide, published a high-quality journal, Structural Engineering International, published books reflected the work of its technical groups, create technical groups, and required by new needs and technical progress, offering the possibility to join activities within national groups of IABSE, offers a program for young engineers, and present annual awards. I think that many of you know that the IABSE award is a very important award, a very important honor for all the structural engineer community. So then I will give a brief introduction of the speaker tonight. So Professor Zhao Shixing is the Chief Engineer of Sichuan Province Architectural Design and Research Institute and a National Class 1 Registered Structural Engineer, a recipient of the State Council Special Government Allowance, a Sichuan Engineering Survey and Design Master, and academic and technical leader of Sichuan Province. His work focuses on the design consultants and research of complex building structures, seismic resilience and design mitigation, and bamboo and timber structures. He had led more than 50 major complex structure design projects and over 20 research projects, contributed to more than 30 technical standards, and received over 50 awards at province level above. Okay, so that's my brief introduction about IABSE and about speaker. So now let's welcome Professor Zhao to give the presentation. Okay, please, Professor Zhao, please.
谢谢陆老师，谢谢主持人。今天非常荣幸哈，非常高兴参加今天这个分享交流。因为我的英语比较差，所以今天委托我们团队的另外一位同事来做这个英文的汇报。
Hello everyone. Can you see our screen?
No, I think you need to switch to another.
Oh, okay. Sorry.
You should share the sliders.
Another screen, right? Wait. I think I
okay, now I can see your screen. Oh, I just saw your screen. You just need to pay patient to wait. Okay, it's beginning. I think everything is going. Okay, I can see your screen. Great. You can start now. Please.
Oh, okay. Hello everyone. I am presenting this project on behalf of Mr. Zhao Shixing and our project team. At first glance, the building appears to be an architecture form inspired by bamboo. But behind that image is a structural question. Can a free-form envelope can become part of the primary load path? The question shapes the whole project. First, let me show you the road through this presentation. The presentation has 5 parts. We begin with the architectural and spatial conditions, then move to the integrated conditions, integrated shear core system, and the main structural responses. After that, I will discuss 4 parallels stability comparison before showing how the geometry was detailed and built. Before we begin, I would like to briefly introduce the research team behind the project. Before we enter the project, I would like to briefly introduce our team. SADI's Complex Structure Design Research Center brings together structure design, engineering consultancy, and applied research. The core team includes 22 young engineers, 3 PhDs, and 16 master's degree members. This combination allows project question to move quickly from design practice into focused research. The center's research direction is anchored by long-term engineering leadership. The center is led by Mr. Zhao Shixing, SADI's Vice General Manager and Chief Engineer. His work span complex structure design, seismic resilience, and applied research. The wider program includes more than 50 major complex projects, more than 20 research projects, over 30 standards, and more than 90 journal papers. This project sits within that broader cycle of practice, research, and knowledge transfer. With that context, let's turn to the project itself. The first section explains where the structure problem came from, the architectural form, the open public space, and the circulation. The building sits in a station-front park and appears to grow from the landscape. Its profile recalls bamboo shoots, and its vertical lines suggest bamboo moving in the wind. But the architectural intention was also spatial. The galleries and the lobby were meant to remain open and largely column-free. They gave us an opportunity. Instead of placing a regular parameter frame inside, we moved the support line towards the envelope. The external geometry could then help carry load, releasing the interior space. The next slide shows how the architectural rhythm became a structural rule. Here you can see the idea as 3 scales. The side image places the building between the railway station, the park, and the preserved bamboo landscape. The section shows the roof rising from the ground with a public walkway. The façade sketch shows curved, non-parallel vertical lines around the roof openings. We did not copy bamboo literally. Its rhythm defines the axis of the curved steel members. Horizontal rings were then added where the floors and the roof edge meet them. So the key move was simple. Architectural line work becomes structural geometry. The internal space then added another set of structural requirements. Here we bring the main spatial requirements together. Around the perimeter, the exhibition floor needs column-free spans of about 13 to 25 meters. The central lobby reaches 30.5 meters with the auditorium floating above it. A public ramp continues to the roof, while the 22-meter-high envelope changes continuously in plan and elevation. Each requirement removes an obvious option. A regular column grid will interrupt the gallery. Columns below the auditorium will bridge the lobby. A constant depth beam would compete with services, and one ramp detail could not suit every location. So the design had to organize several load paths without giving up the open public space. The floating auditorium makes these conflicts especially clear. The auditorium was designed as a room within a room. A daylight gap makes the enclosed volume appear to float above the lobby. Structurally, the obvious supports are removed. Continuous columns through the center would interrupt the lobby and weaken the intended separation around the auditorium. The auditorium is circular, while the available supports are discrete and irregular position. So the question is, how do we support a large occupied volume, keep the space below column free, and preserve the daylight gap around it? Together with the other spaces, this gives us 4 structural questions. The architectural condition can be translated into 4 questions. First, how do we carry gravity load across changing exhibition spans? Second, how do we support the auditorium above the open lobby? Third, how do we support a continuous roof ramp as its support change? And fourth, how do we provide lateral resistance without asking the irregular shear to carry the seismic demand? The questions are connected. Floor beams feed reactions into the shear, slab restraint, and curved members. The auditorium works with the internal frame, and the ramp must remain compatible with the surrounding structures. So we need one coordinated system, but with a clear division of role. That system is subject of the next section. We have now defined the architectural condition. The next question is, how do they become one coordinated structure system? I will begin with the envelope, and then bring in the core, the floors, and the internal frame. Here you can see how the facade grid becomes structure shear. First, the architectural lines become curved steel columns. The larger facade line use 400 by 600 mm box sections. The smaller lines use 200 by 600 mm sections. The key point is that the section family follows architectural line width. The complete arrangement was then checked structurally as part of the shear. Typical spacing is about 3 meters. For horizontal, member families connect and restrain the verticals. Floor ring beams, ties across open zone, intermediate ring and roof ring trusses. Together, these members create one continuous shear. The verticals carry gravity load, while the rings and ties connect neighboring members and reduce their unsupported length. The shear then works with the core, floors, internal frame. Now the shear becomes part of the larger system. The model brings together 3 principal subsystems: the perimeter curved steel shear, the concrete core, and the C-shaped walls, and the internal auditorium frame. Their roles are different. The shear carries gravity load and defines the envelope. The core provides the main lateral resistance. The slab collects load, acts as a diaphragms, and restrains the shear. The internal frame provides the auditorium. Now follow the load path across the bottom of the slide, from the floor and roof, through the beam and rings, into the shear and core, and finally to the foundation. The next slide will quantify how this load is shared. Under the standard gravity combination, the concrete core wall carries 49.6% of the total vertical reactions. The internal columns carry 22.6%, and the curved shear carry 27.8%. The last number matters. The shear is not simply holding up the facade. More than 1/4 of the vertical reaction passes through it. It restrains, joints, and stability, therefore need careful study. These first 3 modes are translation in 2 principal directions, followed by torsion. The period ratios is 0.86 and 0.8, shows reasonably balanced horizontal stiffness for such an irregular geometry. Under seismic action, however, the load sharing pattern is intentionally different. Before looking at the force redistribution, let me state the seismic design basis. Under the Chinese seismic code, the project is in the standard seismic precautionary category with the intensity of 7. A design basic ground acceleration is 0.1 g. Earthquake group 2 and site class is 2. Under seismic action, the country core carries 91.8% of the base shear in the x direction and 90.8% in the y direction. It also carries more than 90% of the overturning moment. The maximum inter-story drift ratio are about 1/2660 and 1/2929. The torsional displacement ratio are 1.38 and 1.32. The result confirms the intended mechanism. The core provides most lateral stiffness and strength, while the shear mainly provides the envelope, geometry, and gravity load path. The shear follows the building lateral deformation, but the core remains dominant seismic resisting component. To make the system work, all design models has to share one geometric definition. Here you can see how the same non-repeating geometry was carried from architecture to fabrication. We extracted the member axes from the architecture facade model and used them as analytical center lines. The same coordinates then control section orientation, connection angles, plate boundaries, and fabrication geometry. A small change in a curved axis can affect the facade model, analytical length, beam eccentricity, and fabricated joints. The parametric model was therefore a shear geometry reference, not just a visual model. The next question is how the floor beams connect to the stability sensitive shell. As a shell, the floor beams transfer gravity reactions and restrain lateral movement of the curved column. A fully rigid end would also send substantial bending moment into a column already carrying compression and geometric relative bending. The detail we adopted transfers shear and gravity load while allowing controlled rotation. It restrains the shear and limits unnecessary beam end moment. This isn't a perfect pin. The joint has a real finite rotational stiffness. Later, we compare rigid, ideal pin, and two practical semi-rigid detail to see how the stiffness affects stability. It also provides erection tolerance, axis for bolting, and welding. With a global system established, we can now look at the main local structure responses. The global system is now clear, but three local conditions still need different structural responses: the long span floor, the floating auditorium, and the continuous ramp. Think of this page as a map rather than the detailed explanation. The underground hall loses its internal columns. The upper exhibition floors lose the regular column grid, and the freeform perimeter lose the orthogonal support line. So each zone needs a different response. A two-way rib floor, taper beam between the core and shell, and a curved shell that below the envelope. The common rule is simple. We match the structural system to the support that architecture removes and the boundary that remains. Let's look more closely at first response, the underground hall. Let's look at the underground hall first. The circular space at the center is about 30.5 meters, column-free public hall. On the plan, the diagonal ribs form a two-way grid. They share the load in two directions and deliver the reactions to the surrounding support. The structure depth is 1.5 meters. The span was achieved without pre-stressing and without embedded structural steel sections. So the important point is not simply the span. The geometry of the grid preserves the open hole while keeping the support around its perimeter. The next condition concentrates on an entire auditorium above the open lobby. The next condition is more concentrated. The auditorium floats above the public lobby, so the direct vertical load path is interrupted. The floor, roof, and enclosure loads must be collected above their void. Central columns can continue through the lobby, and only 7 perimeter support positions are available. The sequence on the right shows the solution. We begin with the 7 columns, add the radial fish belly trusses, and then stabilize the complete auditorium frame. The auditorium is about 26 meters in diameter and 12.6 meters high. The main trusses are 2.7 meters deep, and most of that depth is contained within the auditorium zone rather than the lobby. The load path is now clear. Auditorium loads move into the radial trusses and then into the 7 columns. The transfer system restores the load path while keeping the lobby column free. The surrounding exhibition floors require a different response. The third response is a variable depth composite steel beam. These beams connect core and shell across span of about 13 to 25 meters. Their depth changes along the span, about 1 to 1.2 meters in the deeper zone, and 0.6 to 0.7 meters near the end. Their variation coordinates 4 needs in one number. It supports the exhibition floors, preserve space for the services, reduce the required floor zone depth, and limits moment transfer into the shell through the end detail. Compared with the initial design scheme, the floor zone depth fell by 0.6 meters. The total building height fell from 24.4 to 22 meters, and structural steel use fell by 28.6%. So this is not only a beam optimization, it is a building level coordination result. The ramp was treated with the same location-specific approach. The ramp looks continuous architecturally, but structurally it is not a one repeated system. Its support condition changes as it moves around the 3 main building volumes. Some segments use hidden cantilever, some connect to the C-shaped shield. The longer roof segment uses a box section ramp between available support, and other locations use hanger or local frames. The design rule is location-specific. Choose the support strategy from the available connection, the local span, and the required architecture clearance. These local solutions still have to act together as one building. We can think of the building as 3 zones: the long span underground hall, the central auditorium and core zone, the perimeter floor and shell zone. What matters most is how this zone connects. At the core floor's interface, the slab transfer diaphragm shear and maintain the deformation compatibility. At the floor shell interface, beams deliver gravity reactions, floor restraint, and the curved members and joint control moment transfer. The auditorium trusses create a local transfer path without interrupting the surrounding floor. This isn't one uniform frame. It is coordinated assembly coupled through a few important interfaces. Those interface decisions also lead directly to the research question. At this point, 4 engineering decisions become 4 research variables. The floor restraint, the shell, fabrication and erection introduce geometric deviation. The beam-to-shear joints have finite rotational stiffness, and global model represents the curved member with one-dimensional elements. So we ask 4 questions. What does flow restraint change? How sensitive is the nonlinear stability factor to imperfection amplitude? How does joint stiffness affect shear stability? And what member level behavior is not fully represented by the global model? This question came directly from the project. We now come to the research core of the presentation, 4 control comparisons of shear stability. These are 4 parallel comparisons. They are not sequenced in which one model replaces the previous one. The first comparison changes flow restraints. The second changes imperfection amplitude. The third changes joint rotational stiffness. And the fourth change modeling scale. Each comparison answers a different engineering question. One selected variable is changed, while the remaining conditions are held consistent with their comparison. The conclusion, therefore, sit side by side. Together, they explain how restraint, geometry deviation, joint behavior, and model resolution influence stability. The global analysis established a clear division of roles. Under the standard load combination, the shear carries 27.8% of the total vertical support reaction. Under seismic action, the core receives more than 90% of the base shear and overturning moment. Stability still governs the shear because its curved vertical member carry axial compression along non-straight center lines, producing bending and second-order effects. Systematic research on the collaborative behavior and stability of this shear core system remains limited, so the study focused on 4 variables. Flow restraint limits lateral deformation and changes the predicted buckling mode. Joint stiffness control the beam. Beam end moment transfer into the curved members. Geometric imperfection amplifies second-order response, and model resolution determines whether flexural torsional behavior is captured. For elastic buckling mode isolates the effect of the flow. M01 applies the flow loads but gives the slab no stiffness, so the shear has no diaphragm restraint. M02 uses rigid diaphragms. M03 uses membrane end elements with actual in-plane stiffness. M04 uses shear elements with both in-plane and out-of-plane stiffness. Everything else remains the same: shear geometry, member property, joints, loading, and support conditions. So this comparison isolates only the representation of flow restraint. Now we look at the effect of the flow. In M01, the slab provides no stiffness. The shear can move laterally at one block surface, so global shear buckling governs as an elastic buckling factor of 40.039. Once flow restraint is included, their broad movement is suppressed. The predicted elastic buckling mode changes to single member or multiple member buckling. The single member factor are 50.790 for M02, 61.813 for M03, and 57.57 for the M04. The multiple member mode occurs at about 73.125. So the flows do more than increase the elastic buckling factor. Their in-plane diaphragm action changes the scale of the predicted instability. The paper therefore recommends an envelope check using both unrestrained and flow restraint models, followed by a local stability check of the critical members. For the imperfection study, the control comparison is M12 versus M13. The 2 models use the same membrane slab, material model, loading, and imperfection shape. The main variable is only the imperfection amplitude. With L over 1000, M12 gives 7.505. With L over 300, M13 gives 6.713. That is reduction of 10.6%. A larger deviation increases eccentricity and amplifies second-order effects, reducing the nonlinear stability factor. M11 provides useful context, but it is not part of this control amplitude comparison because its extreme and imperfection condition differ. This comparison demonstrates the sensitivity of the predicted nonlinear stability factor to geometric imperfection amplitude. It therefore supports careful control the consistent representation of fabrication and erection tolerance. The nonlinear model includes both geometric and material nonlinearity. PM2 M3 interaction hinges are assigned at the ends of the curved vertical rings and ring members. At lower loads, the response remains close to elastic. As load increases, plastic hinge develop as selected member ends. Their tangent stiffness decreases. An internal force redistributes to the core and steel elastic member. Eventually, the combined hinge pattern form a mechanism. So the nonlinear limit state is progressive. Member unyielding, stiffness loss, force redistribution, and mechanism formation. First, look at the two practical beam to shell details. Their calculated initial rotational stiffness are 18.3 and 27.1 meganewton meters per radian. But the year 1993 reference limit depends on the connected beam. It is 11.9 for the 7-meter beams and 39.8 for 22-meter beam. The same connection detail may therefore be classified differently. Pin for the 22-meter beam, but not for the 7-meter beam. Now compare the 4 global model: rigid, ideal pin, single plate, and double plate. Their stability factors are here. The result is counterintuitive. The rigid joint gives the lowest factor because it transfers more beams end moment into a compressed curved member. The ideal pin gives the highest factor with the practical details between those limits. For this system, more restraint does not necessarily mean greater global stability. The actual moment rotation behavior matters more than a simple pin or a rigid member. The final comparison asks whether the global beam model can capture the critical member behavior. The multi-scale models start from the M13 nonlinear condition. The loading, imperfection amplitude, and the global boundary conditions remain the same. The curved vertical members in which the first plastic hinge appeared was refined with shell elements. The rest of the building remained modeled with the beam elements. The global beam model predicts a factor of 6.713 and a manufacturer buckling. The multi-scale model gives 5.490, 18.2% lower, and reveals lateral torsional buckling. That does not make the global model wrong. It remains essential for overall load sharing, deformation, and local critical region. The refined model adds member level behavior that a one-dimensional element cannot fully represent. The two models therefore answer different questions and work together. Let's now translate the 4 comparisons back into the design decision. First, represent different actions explicitly. Otherwise, the model may predict global mode that the flaws suppress. Second, derive the imperfection shape from the relevant elastic buckling mode and check justify amplitude. including L over 1000 and L over 300. Third, represent the actual rotational behavior of the beam shear joint. For this system, greater restraint transfer more bending into compressed curved members. Fourth, use member level or multi-scale verification where flexural torsional coupling may govern. These are not a universal ranking of model. They are 4 focus checks linked to the 4 observed mechanism. We now move from analytical verification to detailing, fabrication, and the temporary state of construction. The shear constraint contains curved built-up members, variable transition, and spatial joints, where several members meet at different angles. These parts can be controlled reliably with isolated two-dimensional joints. The parametric model defines center lines, local coordinates, plate boundaries, and connection angles from one dataset. The image shows the process from geometric definition and local analysis to detailing, short fabrication, lifting, and inspection. Components were divided according to the plate forming capacity, transport size, lifting weight, and accessible site connections. Wheel axis and assembly direction were considered during the detailing. Trial assembly and dimension inspection check the physical components against the digital geometry. So parametric model control was directly connected manufacturability and quality assurance. The sequence on site was just as important as the component geometry. The inward curved columns are slender and typical to position along. If erected first, the upper nodes would have limited control and little temporary restraint. So the project used a beam first sequence. The horizontal beam were installed and surveyed first, creating stable reference level and temporary restraint points. The curved columns were then positioned between them. At each stage, the temporary structure was checked for node position, restraint, member force, and deformation. Ring members and the roof trusses were then added to complete the shear action. The final stage was reached through planned temporary states. Construction sequencing was part of the structure and geometric control strategy from the beginning. The next page shows the process in the actual building. Here we move from the plan sequence to evidence from the site. On the left, the auditorium transport system remains temporarily supported, while the surrounding frame is connected. In the center, curved shear members are erected against the established floor and beam levels. On the right, the upper ring is being closed and surveyed. The two details below show the same control and connection level. Well fit up, continuity and axis were checked before closure. Congestive reinforcement and anchorage flow were coordinated before casting. The completed shell therefore emerged through control temporary support, repeated geometric check, and local quality control. The project question also produced knowledge that could be reused beyond this building. The work continued beyond the completed building. Research on the curved and twisted hollow section members, the shear pulse system, and digital construction lead to journal papers. It granted inventions patent and 3 beam and digital design awards and software copyrights. But the point is not simply to list awards. Project-specific problem became protected method, peer-reviewed knowledge, and reusable digital workflow. In this way, design questions become methods that other teams can examine, adapt, and improve. I would now like to return to the title of the presentation. Let me close by returning to the growth of the structure. Architectural reason became the load-bearing geometry because the load path was considered early, moving the support into support line towards the facade preserve the open interior, while the shear carried 27.8% of the vertical reaction. The integrated system then relied on a clear division of the roles. The shear, core, floor, transfer system, and joints work together, while the for comparison identify the mechanism governing stability. Finally, the same structure idea remained consistent through analysis, detailing, fabrication, temporary support, and closure. The engineering question also continued into research and reusable method, and the structure grew from architectural reason into a glide path, from a load path into built reality, and from built reality into transferable knowledge. Thank you very much. We look forward to your question.
Okay, thank you for the very nice presentation, and thank you for Professor Zhao to prepare this very interesting project. So yeah, is there any question from the audience? You can input your question in the chat box, and I will pass the question to the speakers. Is there any questions? Okay, as we are waiting for the question from the audience, I have a question that for the nonlinear simulation of this project, you are using the sub 2000 software. Then how do you consider about the joint for this building? Can sub 2000 have this ability to simulate the joint behavior of this special building? This is my question, please.
You mean the semi-rigid connection, right?
Actually, I'm not an expert on timber building, so I'm just interested that there must be something different from the steel ones or the concrete ones. Yeah.
You mean the joints, right? The
Yeah.
connection.
I mean that how you model the joint, how to simulate the joint behavior of this very special building, very beautiful building.
Joint behavior.
节点行为你们是怎么考虑，就怎么模拟的，在那个非线性分析里面。
It's joint connection, right?
Yeah.
As a pin, right? We model the beam connection to the ideal pin, the perfect pin, and after that we found the rotational stiffness will affect our stability of the curve shear. So we calculate based on the year 1993 to calculate the rotational stiffness and input in the. I think we use we input the stiffness into the joint and then do the calculation.
Okay, so you input the joint one by one for the entire.
Yeah, do the one by one.
Okay. Yeah, that is a very challenging but very, very interesting topic. So is there any yeah, go ahead, please. Sorry.
I think that one we can do we can input through the Excel. They have the interaction model from the Excel. So we do the calculation for each joint. Each joint we have the different label. So we input from the Excel and do the automatic calculation.
Okay, I see. Very, very, very smart job. Very good. Okay. So is there any further question from the audience? Okay, I have a question. Oh, so I will pass this question to you. So I think maybe you can directly see the question in the question box. So the question is, the steel grid shear looks quite complex. How did you optimize it for both structural performance and construction? 就是那个钢效看着很复杂，对吧？就是怎么
Yeah, I see the question.
Yeah, okay, go ahead, please.
Firstly, we have the Rhino to do the shape. We use the software Rhino and Grasshopper to do the shape, and then we try the different shape and to make it like more perfectly. But in this project, the architecture is very important. So we need to follow the architecture reason. We cannot do much for this reason. I mean the shape. So we need to follow that shape. But for the construction, firstly we have the beam model, where the beam model will check with our random model, and also we have the construction method. We erect the beam first, and then erect the column. So this makes like the fabrication and erection on site is more precise.
Okay, very good and very clear answer. So is there any further question from the audience? Okay, I think your presentation is very clear and there's no more questions. Okay, so I think we have finished the presentation and the question and answering process. So is there any further process we need to do? Okay, if there's no more questions and no more further process, so let's end today's webinar. So thank you for Professor Zhao to give this very good presentation, and thank you for the all. Oh, okay, we have one more thing. Okay, no more other questions. So thank you, Professor Zhao, for this very nice project, a very nice presentation. And thank for all the audience here to attend this presentation and give the discussion. Okay, so bye-bye. Bye-bye. Thank you. Bye-bye. Bye-bye.